Well, welcome back, everybody. This is the beginning, I believe, of the 11th week. So we're getting there. These chapters we have pretty small. I'll finish up chapter 12 today, and then I probably won't jump into 13. I'll probably finish a little bit early, and then Thursday we'll jump into 13. Okay. So any questions coming up to now? All right, well, let's get with where we left off, and we have been talking about the concept of the mole. Now, this concept of the mole is something that's gonna come back. We're not done with it. It's gonna be used quite often. Okay. Now, the mole is our connection factor. I cannot go from grams of one reactant to grams of another. What I need to do is I need to convert them both into a common factor, and that common factor is moles. And for some reason, we have no trouble understanding the concept of a dozen, probably because we use it so often, right? We know that a dozen is 12, and the mole is nothing more. Let me regroup there. And if I said to you half a dozen, you know that's 6, quarter dozen, 3, etc. Okay. The mole is very similar. It's just a number for a quantity of whatever you want to count, be it atoms, be it tomatoes, be it whatever. It's just a number. It just so happens to be a very, very large number. Okay. Now, the reason we have to use moles is as follows. Let me explain here real quick. If we have, a general, I'm going to give you a general chemical equation where we got A plus B reacts to give you C plus D. Don't really care what they are, but it's some reactants. Now, if we started off with 10 grams of A and we ended up with, 5 grams of C, and 10 grams of D. Can anybody tell me how many grams of B did we start off with? Keeping in mind, conservation of mass. Who can tell me what this magical number is based on what I gave you here? 10 grams of A, 5 grams of B, 10 grams of D. Remember when we were balancing equations, we had to keep track of all the atoms. If we started off with 10 atoms of whatever, it's going to be 10 atoms of whatever at the end of the day, okay? And those atoms could be, if I start off with 10 grams of anything, I should have 10 grams of whatever I make at the end of the day. And so how many grams of B would I have started off with if after the reaction I measure out 5 grams of C and 10 grams of D?
5.
You got it. It's 5 grams because the conservation of matter tells us that we don't destroy matter, we don't make it, we just move things around, okay? And so here, 10 grams of A requires 5 grams of B to give me 5 grams of C and 10 grams of D. And that's fine if we know all that information. We got 4 variables here, 4 unknowns, but generally what happens is we don't have that information. Okay, what we do is we start off with, let's say 5 grams of A, and we need to calculate how many grams of B. Okay, that may be the question. Or we may have to calculate how many grams of C do we have, or how many grams of D can we make, okay, given that we got 5 grams of A. Well, we can't do a direct weight-to-weight relationship. We need to convert that 5 grams into moles, okay? That's our common factor. And then once we know the moles of A, we can then calculate and determine the moles of any other reactant. whether it be B, C, or D. And once we know the moles of the other reactant, guess what? We can now go back to grams of the other reactant. So moles is a very, very important property that we need to really grasp a hold of with respect to all our calculations that we're going to eventually be doing. So we went through that example in the previous slide, and we showed you here. The takeaway here is this: if I'm given grams and I need to go to moles, I divide by the molar mass, right? And if I have moles and I need to go to grams, guess what? I multiply by the molar mass, okay? And that is basically what we did here. Here, for example, the water. So we have moles of water, we needed to go grams of water. Guess what? We multiply by the molar mass. Here we had grams of silver. We needed to get to moles of silver. Guess what we did? We divided by the molar mass, okay? All right, so much for that. That brings us to something new. Way back when we were looking at properties of the physical state, solids, liquids, and gases, I stated that the volume, with respect to volume, gases did not occupy a specific volume. Okay, they just took the volume of whatever container there is. You know that solids, we can calculate or determine the volume of a solid. And the same is true with a liquid. We just put it in a measuring device and measure its volume, okay? But with gases, we can't have that property. Now I'm telling you we can under only a certain set of conditions, okay? And those conditions we call STP, which is standard temperature and, hold on one second, standard temperature and pressure. The standard temperature is 0 degrees Celsius, freezing point of water, okay? And the pressure is 1 atmosphere. And we here in Tempe, Phoenix, we're in Phoenix metro area, approximately 1 atmosphere of pressure. You go up to Colorado, up high, the atmosphere is a little bit less, okay? So, but under those conditions only, at 0 degrees in 1 atmosphere, we have this relationship here in the far right column. For 1 mole of any gas, it has a volume of 22.4 liters, okay? Only at STP. So if we look at all the gases given here, we have hydrogen gas, fluorine gas, ammonia, xenon, and methane, okay? Those are just my things here for a second. Okay. And so for all these gases, whatever they have, whatever it is, if I have 1 mole of each one, it will occupy, or have, I should say, Avogadro's number with respect to the number of molecules. So like any other mole, 1 mole of hydrogen gas will have 6.02 times 10 to the 23rd molecules of hydrogen gas. 1 mole of methane would have the same number, okay? Now, obviously, they're all going to have different molar masses because they're different elements, different weights, different number of protons and neutrons, etc. So obviously, you know, hydrogen is going to have a molar mass of 2.02 grams per mole, okay? Just like the example with the eggs. We got a dozen eggs of small, yeah, we got 12, okay, 1 dozen, but they're going to weigh a lot less than a dozen medium, right? In both cases, we got 12, but obviously the medium ones are going to have a different weight because they're larger. And so at those conditions, every one of these have this property in that 1 mole of gas, it would occupy a volume of 22.4 liters, okay? So think about that here. That's a ratio. That's another ratio that we have with liters in the numerator, moles in the denominator, or you can take it and invert it, okay? But now you have a capability of, given a volume of gas, under these conditions, we can calculate the number of moles of that gas. And from the number of moles and the molar mass, we can calculate the weight or the mass of that gas, okay? Also, 22.4 is a measurement, okay? It is a measurement, and like given with all measurements, there's a degree of uncertainty. Therefore, if there's a degree of uncertainty, they will be a factor with respect to significant digits. Molar masses do not play a role in determining the number of sig figs because, again, they are the average of whole numbers. And therefore, being the average of the weighted average of whole numbers, they have an infinite number of sig figs. But it does bring me to the point when it comes to molar masses / atomic weights. Do use the atomic weights that we have with respect to our periodic table. Atomic weights, molar masses can differ a little bit if you Google things out. And what happens if you use those numbers in your calculations, they may not correspond. You might be off a digit or two with respect to answers on Canvas. Okay, our answers on Canvas are based on the atomic weights of the periodic table. Okay. All right, so that's the relationship. Let me clear up the mess here. And so we can utilize that ratio in our calculations. This is just a rehash, you know, that at all gases, all at STP, it's important, only at STP. So they may mention in the problem, you are at STP, and that's great, boom. However, sometimes you may see problems where they don't mention the word STP, but they give you 0 degrees in 1 atmosphere. That should tell you, I'm at STP. I can utilize this relationship right there, 22.4 liters per mole. Okay. How do I utilize that? Well, let's try a couple of problems. That relationship, again, as any relationship that we have been working with, any conversion factor is a ratio that we can utilize either with liters on top or liters on the bottom. Which one we utilize depends on the question and what units you are looking for, okay? And so we have the first problem here that says, what is the volume of 1.25 moles of argon gas, okay? Now, normally when I have a problem and I see, you know, reactants here, what I do just as a habit, I just very quickly take with them and verify this. I write down its molar mass or atomic weight just in case I need it. You don't have to. I mean, that's just my little thing. In case I put it there, but notice something when you write down the atomic weight. If the question, if there's no grams question in here, probably more likely you don't need it, but I write it there anyway just to get it ready in case I do. All right. They're telling me I'm at STP, so that's good because I can use that relationship now, okay? And they want to know the volume, identify what I'm looking for. I want a volume here. Well, have we done any other problem? We write down what we are given. We have 1.25 moles of argon gas, okay? And we are looking for the volume, which we're going to use liters. What is the liters of the argon gas? Okay, so obviously we're going to need a conversion factor here of some sort. And how am I going to set that up? Well, I'm looking for liters, so that tells me liters will be in the numerator. I start with moles, so tells me that in that conversion factor, moles would be in the denominator. So because now my moles cancel, okay? So I got the unit set up. Now it's a matter of plugging in the numbers where they belong. So we are at STP, it's 22.4 liters per 1 mole. Thing to notice here about the number that you're going to eventually calculate. You start off with 1.25. That's a 1.25 mole. That's greater than 1 mole. That means that your answer is going to be a little bit bigger than 22.4. Anything just a little bit bigger, not a lot. Okay, so anything less tells you may have set the problem incorrectly as far as the mathematics. Anything greatly more would tell you, I better check my numbers and maybe I punched in the wrong number. So 1.25 moles based on this relationship says I'm going to be somewhere, who knows, well, let's figure it out. Let me clear it up. Okay, set that up, and guess what? We are at 28 liters, at 28.0 liters. Okay, because again, two things. The 1.25 is a measurement, and also the 22.4 is a measurement, but both of them have 3 sig figs, so our answer should have 3 sig figs. Our answer is 28, which is reasonable given that we have 1.25 mole, so it should be slightly greater than the 22.4, okay? And so, again, when you work the problems and look at your numbers, the numbers make mathematical sense based on what you did to them mathematically. All right. Next question. How many moles? Okay, so we're looking for moles here. Is 30.4 liters of oxygen gas at STP. And again, because I'm just a creature of habit, I put 0.32 grams per mole. Okay. Now, given I got 30.4 liters of O2. Obviously, I need a conversion factor here. I need liters in the denominator and moles in the numerator. Okay, I am still at STP, so I can still utilize that relationship of 1 mole per 22.4 liters. Okay, so now you're going to take 30.4 divided by 22.4. That should give you the number of moles. Bear in mind, 22. You know that at 22.4 you have 1 mole. You're at 30. It's just about what, 6, 7 units or so above. So you're probably going to be close to a little bit over a mole with respect to your answer. Okay. Yeah, and you end up with 1.36 moles, which is reasonable given the volume that we started to work with. Wasn't that drastic, greater than 22. Also, our sig fig is 3. We got 3 sig figs at 30.4, 2 sig figs at 22.4. Our answer should have 3 sig figs. So about 1.4, almost 1.36 exactly moles. That corresponds to 30.4 liters of oxygen gas at STP. If the problem you're given does not give you STP or state 0 degrees in 1 atmosphere, your only answer is cannot be calculated, okay? Because this relationship is only true for that condition. All right, now here's the thing here. Let's work this problem out here. They're asking you, what is the mass? So we're looking for mass of 4.5 liters of chlorine gas. Okay, chlorine gas. So keyword gas, obviously chlorine is Cl. We know that it didn't say chlorine atom, they said chlorine gas. So that means it is diatomic. So that's the formula for chlorine gas. And why do I need the formula? Because it looks like I'm going to need the molar mass because they're asking me mass. Okay. And so I have each one's 35.45. So that means 70.90 grams per mole is the molar mass for chlorine gas. We are still in STP, so I can utilize that relationship. All right, so we write down what we're given. We got 4.50 liters of chlorine gas. Okay, we are looking for grams of chlorine gas. All right, so we start off at liters. We're at STP. Guess what? I need to use that relationship, but whereas 1 mole is equal to 22.4 liters, okay, for chlorine gas. So the liters cancel. That leaves me in moles. Here's our common factor. Right here, I got volume, and I got to get to weight. Well, how do I combine the two? I combine them. How do I get from volume to weight? I get there by the units of moles, okay? And so this first factor converts the volume of chlorine to the moles of chlorine. I'm not at grams, so I need one more factor, and I need that factor with the numerator G, grams and the numerator, and moles in the denominator. And that is the units of molar mass. Okay, my moles cancel. It's the molar mass of chlorine gas. Unit-wise, I'm left with G's, which is what I'm looking for. So I have set up the problem properly. Now it's a matter of you plugging in the numbers and see what you get. Okay. All right. Now in this case, sig figs can come from either 4.50 or from the 22.4. They both have 3 sig figs, so our answer should have 3 sig figs, and that is the case. And so 4.5 liters of chlorine gas, large volume, will weigh 14.2 grams. Okay. This flow chart, we're going to give you another flow chart in the next chapter that encompasses this plus some more. And so that helps you work through the problems when we start. Normally what happens is you're either given grams and you want to get your grams of something or some reactant, and you want to get to grams of some product. Okay, or you want to get to volume liters of some product. Okay, well, we have this flow chart to help you out. The point here is that you can't get anywhere without going through moles. Okay, going directly from here to here will not function. That's okay. Getting to the volume will not function unless you go through moles and down that way. Okay, getting from the grams all the way across to atoms, okay, also not a direct route. You have to go through moles. Now this is, I'm moving from left to right, but keep in mind, you can go the opposite direction. I can go from volume to atoms. That's a two-way arrow here. Or I can go from grams to volume. Okay. But I can't do any of that without first having to go through moles. And the connecting factor of moles is what? Molar mass, and if you're STP, 22 liters, 22.4 liters per mole. Okay. All right, let me clean it up. All right, so let me restate something else. Grams to moles, molar mass. Moles to molecules, atoms, whatever units, Avogadro's number. Okay, grams to volume at STP, at STP only, utilize the 22.4 liters per mole. Okay. All right, so let's do an example of one. So here we have the questions: how many grams does 17.35 liters of neon gas mass? Okay, so I have liters and I'm trying to get to grams. So I got grams written here. So neon, maybe I might need a 22.18 grams per mole. I need the molar mass, atomic weight. We are at STP, so I might need to incorporate the 22.4 liters per 1 mole. Okay, so I'm making a list of everything that I have and what I know, and then once I'm there, then I start with writing down what I've been given. 17.35 liters of neon gas, okay? And I need to get to grams. Okay, so that's tells me, that's my map. That's the direction I need to go, from liters to grams. Well, obviously I cannot go through anything from liters to grams without getting to moles. And the only way I can get rid of moles is realize that I'm at STP. And so that's 22.4 liters in 1 mole. So my liters cancel out. I'm good there. Now I'm in liters of neon gas, moles in neon gas, unit wise. Now I got to get to grams. Grams is moles in the denominator, grams in the numerator, because I got moles to cancel. And obviously that is the units of atomic weight. So 20.18 grams per 1 mole. I set it up properly, unit wise. So it's a matter of plugging in the numbers in your calculator and see what you got. So that's what I did here. I write down what I'm given. Unfortunately, I gave you the answer, but that's okay. I'm looking for grams of neon. And so I put in my first factor to get me out of liters and into moles. And then the second factor gets me out of moles and into liters. Okay. So you can see how you can have two dissimilar, on the surface, totally two dissimilar units and still be able to get from A to B, but only through a common factor, which in this case is moles. Okay. So, second question was, how many atoms is this? Well, again, writing down what we're given, writing down where I need to go unit-wise, and which is atoms. I put in my factors. My first factor, like the first step, was to add my 22.4 liters per mole relationship. That gets me into moles of the gas. And then Avogadro's number comes into play. Okay. Avogadro's number comes into play because now notice I can keep track of your units as you go along. See, my units are all canceling out like they should, leaving me with the units that I'm looking for. Okay. All right, and then it's a matter of plug in the number into your calculator, and there you go. Keep track of your sig figs, and you're good to go. All right. All right. Any questions about those? This relationship at STP 22.4. It's another arsenal in the tools, the conversion factors you have access to. Okay. Now, bear in mind here, these examples we have done, the molar mass and the our atomic weights was only utilized one time right here. Okay. because the question asks for how many grams. And when they do that, you're going to end up putting the molar mass in their atomic weight. Number of atoms, nothing was utilized here with respect to atomic mass or molar mass. Okay? And even back here. Okay. We talk about argon gas, but no atomic weight utilized here. So read the questions carefully. Sometimes I've seen examples where the atomic weight was put in twice. Once you put it in to get the moles, and then had to get rid of it later on. You know, read the question carefully. You know, you don't need to use the atomic weight or molar mass every time. Okay. So. This brings us to density. Density is something we talked about before. Density, again, another ratio of simply mass over volume. The densities we talked about earlier, the units were grams over milliliters. When we talk about gases, their units are normally grams over liters, okay? Because this is only true, what we're going to do here is only true, again, if you are at STP. And you can actually calculate the density of gas and not even actually have to measure it, okay? Because, let me explain here. You know, if I take a fraction like 1/3 and I divide it by, I don't know, let's say 1/6, right? Remember that I take that fraction in the denominator and I invert it. So it's 6/1. And so now I got 6/3. Now that's equal to 2, right? I took the fraction in the denominator, I inverted it, and then I multiplied it through. Okay. We're essentially doing the same thing here with respect to the units. If we look at the molar mass, we got grams over mole. Okay. And we're dividing by the molar volume, which is 22.4 liters per mole. So I invert the denominator with respect to units. So I got my grams over moles divided by, multiplied by moles over 20, I'm going to say X here because that's the molar mass, by 22.4 liters. Guess what? My moles cancel. Now I got the units of grams over liters. X is whatever the molar mass is of the material. And so I've been able to calculate or determine the density of gases if they are at STP and if they're only if they're at STP. Senior moment there was going to add something, but I let it go. Anyway, so for the density of ammonium, obviously we need to determine its molar mass, and we've been doing that with some examples. We got 1 nitrogen, 3 hydrogens. That adds up to 17.4 grams per mole. That is the molar mass. And we divide that by 22.4 because that is the molar volume. Therefore, the density of ammonia is 0.761 grams per milliliter. Not to be mistaken with what we were doing before, we had grams per milliliter, okay? This is grams per liter for gases at STP. And you can convert that 0.761 into grams per milliliters if you want, just one more conversion factor. All right. Which brings us to almost getting done with this. Percent composition. Now, in the past, when we were coming up with molar mass, we went through that exercise of adding up, excuse me, all of the atoms involved in that formula, okay, to give us a total molar mass. So now what we're going to do, if you take the contribution of each atom, however number of each atom in the compound they bring in, and divide it by the molar mass and multiply that by 100, you get what is called the percent composition. So if we look at H2O, okay, 2 hydrogens, 1 oxygen. We have a molar mass of 18.02 grams per mole. Correct the units here. These should be grams per mole. I just noticed it's a typo. Okay, grams per mole. All right. We know there's 2 hydrogens. Each total weight for hydrogen is 2.02. Divide that by 18.02 times 100 gives you 11.2% for the hydrogens. Okay. Do the same for the oxygen. 16 divided by 18.02, and that is grams per mole here. And what happens is these units all cancel out. So percentage is unitless other than the percent symbol. Okay, times 100. And we end up with 88.79% oxygen. And so for any molecule of water, and you take it, analyze it, and it will come back as 11.2% hydrogen and 88.79% oxygen. Those numbers should add up to 100%. Now, a quick note here. Notice here, we really can't deal with sig figs when we're doing this. Why is that? Because we are taking atomic weights, which again have infinite number of sig figs, okay? And we're dividing by atomic weights, which have an infinite number of sig figs. So when it comes to percent composition, the general rule of thumb is just keep it to 2 decimal places. Why is that? Because so this one should be like 0, because the number of decimal places we give you in the atomic weights of our periodic table are at 2 decimal places. Okay, so keep it at 2 decimal places. Not concerned about sig figs when it comes to percent composition. In fact, literally almost whatever number you put in technically should be correct because you have an infinite number of sig figs. However, again, Canvas calculates its numbers based on the digits in the periodic table that we hand out to you. Okay. So if you ever do one of these calculations and you're off like 1 or 2 numbers, I'm talking like you're off like 0.01, 0.02, shoot me an email. Definitely will give you credit for that. There's no question. But if you're off like 20 units of 20, it's a totally different story. I think your math may have been incorrect. Okay. All right. So that's how we calculate the percent composition. In fact, every time in my days of synthesizing compounds, once we did all the analysis to figure out the structure of it, and then we did a percent composition, and we sent the sample off for analysis. And if you did it correctly, and the percentage comes back based on your interpretation of the data that you have for the structure. And 9 times out of 10, I did okay. I missed 1 or 2, but it's okay. Doesn't count. I was a graduate student. I was learning. All right, here's an example for you. Find the percent composition for TNT, okay? AKA trinitrotoluene, AKA, anybody know what that is? Dynamite. All right, this is dynamite. This is the formula for dynamite. Not the structure formula, but the general formula. It is extremely difficult to make, extremely difficult, not to mention hazardous to your health. Side note on this, anybody by chance know who is responsible for making the TNT compound? Very famous scientist. You might be familiar with his name and not even know it. There's a weekly award, an annual award. It's a prize for medicine, chemistry, physics, literature. Anybody know what that prize is called? Peace. But surely you know what that prize is called. Nobel. Okay, Nobel Prize. Nobel was a chemist. He's the one who developed this. And because of that, he just made a ton of money. And a lot of that money was eventually utilized to create the Nobel Prize. All right, so what do we do here? Like, that's just like we did with water. Identify how many of each atoms you had. Remember, we did way back when we were giving you formulas and we're asking you, well, how many atoms do you have in the whole formula? And you had to figure out how many nitrogens, how many oxygens, etc. So, well, here we are again. Okay, so we got 7 carbons, 5 hydrogens, 3 nitrogens, and 6 oxygens. Okay. And using the periodic table from our the atomic weights from our periodic table, 7 carbons at 12.01 gives you 84.07 grams per mole. Hydrogen, 5 of them at 1.01 gives you a total of 5.05. Nitrogen, 3 of them at 14.01 gives you a total of 42.03. And six oxygens at 16 apiece gives you a total of 96.00. Tally it up, you have a total molar mass of 227.15 grams per mole. So again, if you were in the lab and very carefully weighed out 227.15 grams, you have 1 mole, or 6.02 times 10 to the 23rd. Okay. So now we having the individual amounts for and the total molar mass, we can figure out the composition. Carbon represents 37.01%. Hydrogen is 2.22%. Nitrogen, 42 over the total molar mass gives you a 18.50%. And then finally at oxygen gives you a total of 42.6% oxygen. All that should tally up to 100%. Okay, so the percent composition, very simply add up all the atoms, individual atoms, and multiply it by that number by the atomic weights for those atoms. Tally all that numbers up. That gives you the molar mass. Come back and do each of the individual atom weight, total weight divided by the molar mass times 100. It gives you the percent composition, which adds up at 100%. All right, well, that brings us to these. Try these at home. I told you we're going to probably be finishing up early, which works out great because I have an appointment that I'm going to get to. And so try these at home. The question here is how many liters will 3.425 grams of carbon dioxide occupy at STP? Okay, so you're at STP. You should end up with a number of 1.74. Notice liters. Notice it has 3 sig figs. The grams is 4 sig figs. So someplace in there, it changed the number of sig figs in your answer. Okay. Second question says, how many molecules are there in the same quantity of carbon dioxide? 3.425 grams of carbon dioxide. And here we have 4.68 times 10 to the 27 molecules for that quantity of carbon dioxide. And then finally, if you have 3.0 times 10 to the 15 molecules of carbon dioxide, figure out its weight. That's a large number, 3.0 times 10 to the 15 molecules. But even with that large number of molecules, the weight is only 10 to the negative 7 grams, pretty small quantity. All right, well, ladies and gentlemen, that brings us to the end of chapter 12. And like I stated, I'm going to stop it here. We will continue with 13, which is fairly short chapter also. We're probably going to end up with a day or so of what I call study days, meaning that I'll still be here at the regular time, but it'll be open. So if you have any questions during that time, it's a good preparation time for for the final coming up, because we're, like I said, we're in the 11th week, which, you know, we got 5 weeks of final, 5 weeks before finals. And really, maybe, you know, we got our Thanksgiving break. So, you know, it's right around the corner. All right. So, any.
Yeah, I had a question about the homework.